Hey guys, my name is IBM and I'm taking you through the tutorials of electricity and DC circuits. And I think today in lesson 6, we shall introduce Kirchhoff's laws. Uh, I think Kirchhoff's laws are the most important concepts, or Kirchhoff's laws are very important in electricity and DC circuits. So in lesson 6, we shall basically concentrate on Kirchhoff's laws. Do not forget the course outline for the AS physics. That is Physics 9702, where you study physical quantities and units, errors and uncertainties, treatment of uncertainties, kinematics, dynamics, force, density and pressure, work energy and power, deformation of solids, waves and superposition, electricity, particle physics, and we are currently trying to finish up with electricity and DC circuits. The units in red have already been covered. You can check the playlists to see the tutorials. Okay, so this is lesson 6, and let us immediately introduce Kirchhoff's laws. We shall begin the concepts of Kirchhoff's laws, or we shall begin talking about these laws by first of all referring to the background of Kirchhoff's laws. So Kirchhoff, I think Kirchhoff is a name. This was called Gustav Kirchhoff. I think Gustav Robert Kirchhoff was a German physicist who contributed to the fundamental understanding of electrical circuits, spectroscopy, and emission of black-body radiation by heated objects. If you're doing both AS and A-level physics at the same time, we're doing two in one, you might have you might have studied already, uh, you might have studied astrophysics and cosmology, where I talked about black-body radiation, any object which absorbs all radiations falling on it without reflecting, but emitting a whole wavelength of radiation. That was a black body. So Gustav Kirchhoff's contribution to science was seen in the understanding of electrical circuits after after analysis of several electronic circuits, as we are going to see. So Kirchhoff got himself a huge name in physics by simply applying two principles of physics to electrical circuits. The principles of physics which we are going to explore under Kirchhoff's laws are the one for conservation of energy and the one for conservation of charge, which we already knew from other topics that we have covered either in IGCSE or in AS physics. For example, we know that charge can neither be created nor destroyed, but charge can leave one object to another object. You might have seen that in electrostatics. You may also have mentioned the law of conservation of energy in a unit called work, energy, and power, where energy can neither be created nor destroyed, but can easily be transformed from one form to another. So, you recall from conservation of charge that the net charge of an isolated system remains constant. It is not possible to destroy or create charge. All we can do is make sure that charges leave one body to another body. So the net charge of an isolated system remains constant. Of course, you can cancel out the effect of charge. For example, you can neutralize the charge on a body by adding an equal and opposite charge to it, but you cannot destroy the charge itself. For example, if I have 20 positive charges, I can add 20 negative charges. If I have 20 excess positive charges on a body, I can neutralize it by addition of 20 negative charges to make total charge to be zero, but I cannot destroy the charge itself. So for example, if a glass rod is rubbed with a silk cloth, due to friction, the glass gets charged positively because it loses the electrons, and the silk negatively because it gains the electrons. So the charge is basically due to the transfer of the negative charges, that is the electrons, from the glass to the silk. So during rubbing of a silky cloth or a glass rod on a silk cloth, the friction is going to cause the glass to get charged positively because it's going to be losing electrons, and the silk negatively because it's going to be gaining electrons. So charge is leaving one body to another body, but the total charge is going to remain the same. So this experiment suggests that charge is transferred but not created or destroyed. It is leaving one body to another body but it's not created. Therefore, the total charge on the glass silk cloth remains the same, that is 0 before rubbing and 0 after rubbing. So that is the law of conservation of charge. Charge is not being created nor destroyed, it is just leaving one body to another. So the total charge of an isolated system is going to remain constant. So that's one of the laws which Kirchhoff considered. And considering that law or that principle of physics, he was able to come up with what we shall call Kirchhoff's first law. Okay, so I'll record that a series circuit is one in which the components are connected one after another, forming one complete loop. An ammeter connected in series at any point reads the same current as we have already seen in other previous lessons. So if we have a circuit in series, the components are connected one after another to form a closed loop. And if we place the ammeter at any point within the circuit, it will always give us the same reading of current. That is very important. However, if the circuit is connected in parallel, if we have a parallel combination or a parallel circuit, for a parallel circuit, the current, as we mentioned earlier on, is expected to divide at a junction. So a parallel circuit is one where the current can take routes in different loops. So in a parallel circuit, the current divides at a junction, but the current entering the junction is going to be the same as the current leaving that junction, because charge, the total charge of an isolated system remains constant. So because current is the rate of flow of charge carriers, we expect that the current which reaches a certain point must be equal to the total current which leaves that point. So if we consider a circuit like this one, which has two branches or which has bulbs joined in parallel, so a current of 3 amperes, say from the battery, when it reaches a junction, we expect that the charges split at this point here. Maybe some charges take that path and other charges take that path. But because current is the rate of flow of charge carriers, uh, the charges divide at this point, but total charge should remain the same. So it means total current should also remain the same. So the 3 amperes is supposed to divide at a junction depending on the size of these resistors. Of course, at the other junction, then the currents are going to recombine to form back the 3 amperes. That is if the circuit is a parallel circuit. So we recall from lesson, I think lesson 3 or 4, that in a series circuit, the current is the same, but in a parallel circuit, the current divides at a junction or it recombines at a junction. And when I talk about current, remember, current is the rate of flow of charge carriers. So it's like the first law is going to relate to conservation of charge. That is Kirchhoff's first law. So let's look at the statement of Kirchhoff's first law. So the fact that current does not get used up at a junction, that is, charge does not accumulate at a junction. Because current is the rate of flow of charge, the charges cannot accumulate at a junction, or the charges cannot get used up at a junction. So the consequence of conservation of electric charge, the consequence of conservation of electric charge is going to be known as Kirchhoff's first law. So the first law is a consequence of conservation of charge. Sometimes it will be called the law of conservation of current at a junction. So Kirchhoff's first law is a law of conservation of current at a junction. It is a consequence of conservation of charge. Total charges entering a junction should be the same as total charges leaving the junction. Because current is the rate of flow of charge carriers, we can say total current into a junction should be equal to total current out of the junction, or the sum of current entering a junction or the sum of currents into a junction is equal to the sum of currents out of a junction. So many times we can even write a summation of IN. This is read as summation, which means the sum of currents into a junction should be equal to the sum of currents out of junction. To illustrate this, let's consider a simple situation where a current I is incident to this junction here and it splits into three currents. Since all the other three currents are leaving the junction, then we can say from the law we have just mentioned that the current I should be equal to I1 plus I2 plus I3. The sum of currents into a junction should be equal to the sum of currents out of a junction. If I was to put all these on one side, then I would say I minus I1 minus I2 minus I3 should give us 0. It means I have considered the currents into the junction positive and currents out of the junction negative. When I consider positive or negative, I'm considering algebra. This is algebraic. So I can simply state this law by saying that the algebraic sum of currents at a junction is 0. Instead of saying currents into a junction equals to the currents out of a junction, I can simply say the algebraic sum of currents at a junction, not into, not out, but at a junction is 0. Because when I say algebraic sum, I may choose currents into the junction positive and currents out of the junction negative. Then when I sum positive and negative, I'm considering the algebraic sum. So the algebraic sum of currents at a junction should be 0, and that is Kirchhoff's first law. So we have said Kirchhoff's first law is a consequence of conservation of charge, and it can also be called the law of conservation of current at a junction. The algebraic sum of currents at a junction is 0, or the sum of currents into a junction is equal to the sum of currents out of a junction. That is Kirchhoff's first law. So in an algebraic summation, a current is considered maybe positive if it is entering a junction, and you can consider it to be negative if it is leaving the junction, or vice versa. So for example here, I may consider currents entering the junction to be positive, and I may decide to consider the currents leaving the junction negative. So I can say this is positive because it's entering a junction, this is negative because it's leaving the junction, this is negative because it's leaving the junction, and this is positive because it's entering the junction. This is negative because it's leaving the junction. So if I use the algebraic summation of all currents at the junction equals to 0, so it would mean I will say positive I1 plus negative I2 plus negative I2 plus positive I3 plus negative I4 should give us 0. That is the algebraic sum. The algebraic sum of all currents at a junction should be 0. You must consider currents into the junction maybe positive, out of the junction negative, or the other way around. You can consider currents out of the junction to be positive and those into the junction to be negative. After all, the algebraic sum will still be equal to 0. So if we simplify this, we just rearrange, leaving those which are positive on one side and take those which are negative to the other side. You will still remain with the fact that I1 plus I3 is equal to I2 plus I4 plus I5. And note that I1 and I2 is the sum plus I3 is the sum of current into the junction. And I2 plus I4 plus I5 is the sum of currents out of the junction. So it makes sense for us to say that the sum of currents into the junction is equal to the sum of currents out of the junction. And we are saying this is Kirchhoff's first law. It is a consequence of conservation of charge. It is a consequence of conservation of charge, or it will sometimes be called the law of conservation of charge at a junction. So in conclusion, Kirchhoff's first rule is a statement of conservation of electric charge, as I've already mentioned. First law is conservation of electric charge, or simply charge. All charges that enter a given point in a circuit must leave that point because charge cannot build up or it cannot accumulate at one point. If charge was to accumulate at one point, this would violate the law of conservation of charge. So if this does not happen, then charges are getting accumulated at a point, or charges are created from nowhere, both of which can't happen. If charge was to accumulate at a given point, it would mean that charge is coming from nowhere and is getting stuck at one point. Yet for current to flow, the charge carriers must continuously be moving throughout the circuit. The same charge carriers must be moving around the circuit. So if the charge carriers get stuck at one point and accumulate at that point, it means if the circuit is isolated, then it means charges are coming from nowhere to that fixed point, which is practically not going to be possible. So that is Kirchhoff's first law. The sum of currents into junction is equal to the sum of currents out of the junction. Let's do a few examples to understand Kirchhoff's first law. In the circuit below, state the reading of the ammeters A1, A2, and A3. So, assuming A is 350 milliamperes, so it means A1 is going to be reading 350 milliamperes because these two ammeters are just linked to each other. Of course, we expect that when current reaches here, we expect it to be dividing. Some of it should take this path and some of it should take this path. But the current taking this path is given as 150 milliamperes. So it means when I get this current plus 150 amperes, I should get 350 because 350 is entering the junction. So let me call this one current A3. So when I say A3 plus 150 should give me 350. That is in accordance to Kirchhoff's first law. So that means A3 is going to be 350 minus 150, which gives us 350 minus 150, which gives us 200, I think, milliamperes. So A3 is reading 200 milliamperes. Then our current which is entering here is 150, which is read with this ammeter here. So 150 at this junction again divides. Part of it takes this path, which is 50 milliamperes, and part of it should take this path, which is read by A2. So the reading of A2 plus 50 milliamperes should give us 150 milliamperes, which means A2 should be equal to 150 minus 50, which is going to be 100 milliamperes. So we have used the Kirchhoff's first law, that is conservation of charge, or the sum of currents at a junction equals the sum of currents leaving the junction. So we have used Kirchhoff's first law to understand or to obtain the current, the different currents. So A1 is the same as 350 because it is just linked to the other one, so they must be reading the same current. And A2 would be, we have seen it is 100 milliamperes, as total current should be 150. And A3 would be 350 minus 150 because total current should be 350. So this is how we use Kirchhoff's first law to find these currents. Okay, example number 2 maybe. So the lamps in the figure are identical, which means they have the same resistance. If they are identical, they have the same resistance. There's a current of 0.5 amperes through the battery. So let's say the current from the battery is 0.5 amperes. So we have a junction here where the current must divide. Because they are two and they are identical, it is going to divide equally. Because total resistance here is the same as total resistance here, so the current divides equally. So because remember the current is always shared or divided in the ratio of the resistances, so this will take 0.25, and this branch will also take 0.25. Because the bulbs or the lamps are identical, the current divides equally. Remember, less current flows in a more resistive path. So if they are identical, then it means the current has no option other than dividing equally. The figure shows one junction in a circuit. Calculate the the ammeter reading. So remember, the sum of currents into a junction should be equal to the sum of currents out of the junction. So here the currents let this current be X. I'll not put a direction. Maybe I can choose a random direction. Let me say in this direction. I'm just randomly choosing the direction. Let me call it I in that direction. So the sum of currents into the junction will be 2 amperes. Should be equal to the sum of currents out of the junction, which is we have 2.5 plus 1.5 plus I. If I is a negative, it means I chose the opposite direction. I chose the wrong direction. So it means I is going to be equal to 2 minus 5, with 2 minus, I think this is 2 minus 4, which is negative 2 amperes. The negative just shows that I chose the wrong direction, so it is supposed to point towards the junction. So the answer will be 2.0 amperes towards the junction. The minus is just emphasizing that I would have chosen another direction other than the one I have chosen in this case. Okay. Kirchhoff's first law still in the above circuit, B1, B2, B3, and B4 are bulbs. The readings of ammeters E and F are respectively. So let's check the readings of these ammeters using Kirchhoff's first law. So using Kirchhoff's first law, if this one is I is 1.3 amperes, so it means the reading of B2, bulb 2 will have a current of 1.3 amperes. So B2 should be 1.3 amperes. B1, B2. B2 should be 1.3 amperes. So this one is wrong. Sorry, the readings of ammeters E and F. Okay, we want ammeters E, and F. Okay, so we don't need B2. So at this junction here, if we say current started from this point, it splits at this junction. Part of it takes this path, part of it takes this path. So at this point here, the current which goes through E, I would say I into E, combines with the 1.3 at this junction to give us 2.6. So I have that at that junction, sorry, I don't need to write B there. So at this junction here, I have that the current which is I, the reading of E plus 1.3, those are entering the junction, should give us whatever is leaving the junction, which is 2.6. So it means the current into E is going to be 2.6 minus 1.3, which is 1.3 amperes. So E should be 1.3 amperes. So this is wrong. Then I can check F. So what 2.6 is entering this junction. So part of it takes this path, part of it takes that path. So the current here is, I'll call it IF. So IF is leaving the junction, and 1.1 is also leaving the junction, but what is entering the junction is 2.6. So IF is going to be 2.6 minus 1.1, which is going to be 1.5 amperes. So it means our answer is going to be B. Let's talk about Kirchhoff's second law. The first law, remember, was a consequence of conservation of charge. And we said Gustav Robert Kirchhoff considered two principles of physics, that is conservation of charge and conservation of energy. The second law is a consequence of conservation of energy. So you recall the law of conservation of energy that we talked about in lesson or in a unit called work, energy, and power, which states that energy can neither be created nor destroyed, but can simply be transformed from one form to another. I think in lesson 2 we mentioned that charge flowing around a circuit gains electrical energy. If you remember Mr. Coulomb, as charge went through the battery, it gained energy from the chemicals of the battery. That's where we had the EMF. And as the charge went through a component, maybe a lamp or a resistor, it lost energy. It lost its electrical energy in the form of light or heat. That is what we call the PD. So as charge flows around the circuit, it gains electrical energy on passing through the battery, of course, from the chemical energy, and it loses electrical energy on passing through the rest of the circuit. And by conservation of energy, the total energy it gives out to the rest of the circuit must be equal to the total energy which is supplied by the power supply. In other words, total energy must remain the same. And this consequence of conservation of energy is known as Kirchhoff's second law. So consequence of conservation of energy is going to be called Kirchhoff's second law. In a circuit, we have 2 points where energy is generated or where energy is mentioned. In a circuit where you have a power supply, that's where we have the EMF. And if I have a resistor, this is where we have the PD. So here, the charge gets energy from the chemicals of the cell. And we said the energy here is, the EMF is the energy converted from chemical to electrical for every charge which passes through the cell. And as the charge continues on its way, it loses its energy to the resistor, for example. And this is where we had the PD. We define the PD as the energy converted from electrical to heat or light per unit charge. So the total energy which is given out to the external circuit cannot be greater than the EMF. So that is conservation of energy. So we can simply state Kirchhoff's second law as the algebraic sum of all potential drops, or PDs, is equal to the algebraic sum of all EMFs. The sum of EMFs is equal to the sum of PDs as long as the circuit is complete, or as long as we have a complete loop. So the loop must be closed, or the circuit must be closed. So there are 3 important things here. First of all, it must be a closed circuit or a closed loop. Secondly, the sum of all the potential drops or all the PDs should be equal to the sum of all the EMFs. So the algebraic sum of all the potential drops is equal to the sum of, or is equal to the algebraic sum of all the EMFs. That is going to be Kirchhoff's second law, which is a consequence of conservation of energy. So Kirchhoff's law therefore means, Kirchhoff's second law therefore means that the energy gained by the charge as it passes through the sources such as the EMF, the energy gained passing through sources of EMF must be equal to the energy lost passing through other components within the circuit, which is going to be the PDs. So the energy gained passing through sources of EMF is equal to the energy lost passing through components with the PDs. And sometimes Kirchhoff's second law will be called Kirchhoff's voltage law. Remember, the first law was the law of charge, of current at a junction. And the second law will be called voltage law, because EMF and PD are both measured in volts. So we can also call this voltage law. So let's consider a simple circuit such as this one, which incorporates a bulb or a lamp with the resistance R1 and a resistor with the resistance R2. Let us assume we have a cell whose internal resistance is negligible. So the cell is the power supply, or is the supply of the EMF. So we assume that the total PDs across the lamp and the resistor R cannot exceed the EMF E, or it cannot be less than the EMF E if the resistance of the wires is negligible. So according to Kirchhoff's second law, the sum of EMFs is equal to the sum of potential drops V. In other words, E is going to be equal to V1 plus V2. You should not forget Ohm's law, which says that V equals to I times R. So it means the potential drop across R1 can also be given as I times R1. And the potential drop across R2 can also be given as I times R2. That is Kirchhoff's second law. So we say that the sum of potential drops or PDs. The sum of potential drops is the PdV1 across the lamp plus the PdV, this is going to be V2 across the resistor. And thus, we just sum up these two and we get V1, because we know that PDs are got from Ohm's law, which is V equals to I times R. So it means V1 is I times R1 and V2 is I times R2. Of course, these are in series, therefore the current through them is the same. Hence, I can simply say the e.m.f. E is equal to IR1 plus IR2, or it can also be written as E equals to I into R1 plus R2. This can also take you back to what we mentioned earlier on, that the current was equal to the EMF divided by total resistance. R1 plus R2 is the total resistance. So the current could also be quoted as the EMF divided by total resistance. However, we were considering Kirchhoff's second law, where the sum of EMFs is equal to the sum of PDs. I have considered a very basic and simple circuit. Okay, so we are still exploring on Kirchhoff's second law. So both EMF and PD have direction. Both EMF and PD are going to have direction, and therefore this is going to necessitate us to have what we shall call the sign allocation to the PDs and the EMFs. In order to apply Kirchhoff's second law, we are going to assign or to give sign allocations to the PDs and to the EMFs in the circuit. So both EMF and the potential difference have direction. And this must be considered when working out the equation for Kirchhoff's second law. So let's discuss the sign allocations to the PDs in a circuit. And this is what makes our life very hard, especially for students when dealing with Kirchhoff's when dealing with Kirchhoff's second law. So PD, potential difference across a resistor, is going to be considered positive if the current is in the same direction as that of the loop. So remember I said Kirchhoff's second law, when you talk about Kirchhoff's second law, you must refer to a closed loop or a closed circuit. So the PD across a resistor is considered to be positive if the current is in the same direction as the loop. I will illustrate this with a diagram. So consider a situation where we have this is where we have the PD. Of course, potential drops are around components outside the battery or in the circuit outside the battery. So the current is flowing in this direction from the left-hand side to the right-hand side. The current is flowing in that direction. If I choose, or if the loop is in the same direction as the current, the PD is going to be considered to be positive. Remember, V is equal to I times R. So if the current is in the same direction as the loop chosen, the PD is going to be positive. I will give an example for that. On the other hand, the PD across a resistor or any other component is going to be considered to be negative if the current flows in the opposite direction to the loop chosen. A simple illustration with this, if we have a current flowing from right to left, so the current is flowing from right to left, but the loop is in the opposite direction to the current. So if the loop is in the opposite direction to the current, or the circuit, the movement around the circuit is in the opposite direction to the current, then the PD is going to be considered to be negative. If if the current is in the same direction as the loop, the PD is going to be considered negative. This is a sign conversion or a sign allocation. And if the current is in the opposite direction to that of the loop or to that of the circuit movement, then the PD is going to be considered negative. I will show this in an example. Let us also talk about the sign allocation for the EMFs, because we said both PDs and EMFs are going to have directions. And therefore, because they have directions, we must allocate them signs in order to easily use them in our calculations. So let's talk about the sign allocation of the EMFs. So still, there are two ways of moving around the cell, or of course EMFs are at around the cell. We don't talk about the resistor when we are talking about the EMF. So if the EMF of a cell is going to be considered positive if the loop moves from the negative terminal of the cell towards the positive terminal of the cell. What do I mean by that? Consider a situation where I have a cell like this one here, and the short bar is the negative terminal and the long bar is the positive terminal. So moving around the cell, I start with the negative terminal before the positive terminal. It means the loop first encounters negative, then positive. The EMF is going to be positive. In other words, the loop is in the same direction as the current from that particular cell, because we know current flows from positive to negative. So if the loop is in the same direction as that of current from that particular cell, remember current is from positive to negative for a particular cell, that means the EMF is going to be negative. In moving around the circuit, I meet negative terminal before positive terminal. The EMF is going to be positive. On the other hand, the EMF of a cell is going to be considered negative if the loop moves from the positive terminal of the cell towards the negative terminal. What do I mean by that? In this circuit, I have chosen a loop which is in the opposite direction to that of the current from that particular cell, because current flows from positive to negative. So it means the current from this particular cell will be in that direction. So if the loop is in the opposite direction to the current which comes from that particular cell, the EMF will be negative. Or if in moving around the circuit, I meet a positive terminal before a negative terminal, then that EMF will be considered to be negative. That is a sign convention. Let's try to use this maybe in an example. Let's use the sign allocations in an example. So in this example, I have two cells. One has EMF E1 and another one has EMF E2. And I have chosen a loop. This is the loop I have chosen. When I talk about the loop, it shows the direction that I have to move around the circuit. So I will label this to be A, B, C, D. So according to the direction of this loop, it means the direction I'm moving around the circuit is say from A to B to C to D back to A. So I am moving around now. If I move from A to B, B to C, C to D, I'm coming to the cells now. I meet a positive terminal before a negative terminal. The convention is telling us that this EMF will be negative. Then I continue on my way. I meet a negative terminal before positive terminal. This EMF is going to be positive. Because naturally, the current from E2 would flow in this direction. Naturally, the current from E1 would flow in this direction. If the current from that particular cell flows in the same direction as the loop, the EMF is positive. If the current from that particular cell is in the opposite direction to the loop, the EMF is negative. So E1 is positive and E2 will be negative. So I have to sum them up. So I will say E1 plus negative E2, or negative E2 plus E1. Then I talk about the PDs. Of course, for the PDs, I look at the components outside the cells. So in moving around from A to B, and then B to C, C to D, D to A, I move in the current through R1 is in this direction. It is in the same direction as the loop. If the current is in the same direction as the loop, the PD there is positive. R2, the current of course is the same as the one in R1. So the current in R2 is also in the same direction as the loop, so the PD here is going to be positive. So in other words, if we consider the two cells connected in opposition, they're in opposite directions, total EMF, or the sum of the EMF, is going to be E1 plus negative E2. That is by Kirchhoff's law. And the sum of the PDs are going to be V1 plus V2. But remember, V is equal to I times R. So the sum of EMFs is going to be equal to the sum of PDs. That is in accordance to Kirchhoff's second law. So we can summarize Kirchhoff's laws using the equations below. In other words, the sum of currents into a junction is equal to the sum of currents out of the junction. And then the second law, the sum of EMFs is equal to the sum of PDs. But of course, if you are stating them in an exam, you must talk about first law, you must mention the junction, and second law, you must mention a closed loop. Okay, these are Kirchhoff's laws. I think what remains is now to use them. Let's try to use these laws in examples. If you understand the sign convention, then you should be able to use them in examples. So we're going to do a few general examples. Of course, for examination purposes, you'll not always be asked to solve these questions deeper, but you'll be able to come up with equations for the currents, or equations relating the currents to the PDs, or the equations relating the EMFs to the PDs using Kirchhoff's laws. So to apply Kirchhoff's laws, many times if the circuit is complex, the examiner will choose for you the direction of the loops, and your task would be just to move around the circuit to see if you can identify the sum of currents and the sum of PDs, or the sum of the EMFs with the correct signs, or with the correct sign conversion, or the correct sign allocation in both cases. So here in this case, we have a circuit like this one where the loops have been chosen. For example, loop 1. For loop 1, we have to move from, say, A to B. We have to move from A to say A to D to C to B back to A. That is the first loop. Then in loop 2, we have to move from B, because loop 2 is anti-clockwise. Loop 2 is clockwise, so it is B to E to F back to C and back to B. That is the second loop. So our task is going to be to come up with equations relating current, maybe at junction at C, or at junction C, or at junction B, and equations relating to the PDs, equations relating the EMFs to the PDs for both loops. That's what we want to establish now. So if you have understood the sign convention, if you have tried to understand the sign convention, you can try to pause the video and see if you can find the sum of currents at a junction, and then the sum of the PDs using the sign convention. So for example, at the junction C, note that the current I1, which is entering junction C, is the same current here, so the current here is still I1. The current I3 is coming here, it is the same current coming here, which is I3. The current I2 is the same current here, is the same current here, is the same current here, so this is I2. So we see that at B, I2 is leaving, I1 is leaving, I3 is entering. So I can say at B, I3 is equal to I1 plus I2. Or I can look at junction C. I1 is entering junction C, I2 is entering junction C. So still I can say the sum of currents entering equals the sum of currents leaving. The current leaving here is I3, should be equal to the current entering, which is I1 plus I2. So it is the same thing. So at junction C, the sum of currents entering the junction is equal to the sum of currents leaving the junction. That's number one. That is Kirchhoff's first law. Then Kirchhoff's second law. Let's try to look at loop A, D, C, B, back to A. So if I consider that loop, I will start with the EMFs. Moving from A to B to D, there is no cell. D to C, there is no cell. C to B, there is a cell. But in moving from C to B, I meet negative before positive, so this EMF is going to be positive. If I meet negative before positive in moving around the loop in the correct direction of the loop, I meet negative before positive. It means I'm moving in the same direction as that of current, which would be coming from that cell. Do not confuse yourself with this current here or with this current here. The correct way of direction of current to flow is from that cell, from a cell is from positive to negative. So in moving around the loop, A to D, D to C, C to B, I first meet negative before positive, so the EMF is going to be positive. Since there is no any other cell in the lower loop or in the lower circuit, so also the sum of the EMFs is going to be positive 10.0 volts, should be equal to the sum of the PDs. So for PDs, I look at the resistors. If the current through a given resistor is in the same direction as the loop, the PD is positive. If the current through the given resistor is in the opposite direction to the loop, then the PD is negative. In moving from A to D, D to C, I'm moving in the opposite direction to the current through the 2 ohm resistor. So the PD is negative. So this would be negative 2 times I3. Remember, the PDV is equal to I times R. Then, in moving from C to B, I'm moving in the opposite direction to the current which goes through 6 ohms, which is I1. So still this PD is going to be negative. So this would be minus 6 I1. So this is the sum of the EMFs. This will be the sum of the PDs. That will be one equation. If I consider another loop, which is loop 2. Loop 2 is say from B, because when you look at the arrows, it is clockwise. So it could be say from B to E to F to C back to B. So the sum of EMFs, so I'm moving from B to E, there is no cell. From E to F, I start with the positive before negative. This EMF is going to be negative, so that will be negative 14 EMF. When I move from F to C, there is no cell. C to B, there is a cell. But when I move from C to B, I start with the negative before positive, so the EMF is positive. So this will be plus 10. That will be the sum of the EMFs in the upper circuit. This should be equal to the sum of the PDs. For PDs, I look at the resistors. From B to E and E to F, F to C, the current through 4 ohms is I2, which is in the same direction as the loop. I say the current here is the same current, here is the same current, here is the same current here. So the current through 4 ohms is I2, which is in the same direction as the loop. And we said if the current is in the same direction as the loop, then the the PD is positive. Remember, the PD is given by current times the resistance. So this will be 4 times the resistance, which is, the current, which is I1. Then E to F, there is no resistor. F to C, there is no resistor. C to B, there is a resistor of 6 ohms. But in moving from C to B, I'm moving in the opposite direction to the current, which is going through 6 ohms. So this is going to be minus. So this will be minus 6I2. Sorry, 6I. No, this was I2 and this is I1. Okay. The current through 4 ohms was I2, not I1. And the current through 6 ohms is I1. The current through 4 ohms is in the same direction as the loop, but the current through 6 ohms is in the opposite direction to the loop. So here the PD will be negative, the other one is positive. So in other words, I can say negative 4 plus 10 is, I think, negative 4. Negative 14 plus 10 is negative 4 equals to 4I2 minus 6I1. So this will be the second equation. If the equations are very short to solve, the examiner may ask you to find I1 and I2 or I1 and I3. But in many cases, you will not solve such equations. If you have a scientific calculator and you want to solve the equations, you can just put them into the calculator because you have 3 equations. The one relating the current, you have this one, and you have 3 unknowns. Scientific calculators can solve equations, 3 simultaneous equations with 3 unknowns very easily. So applying Kirchhoff's junction rule, we got that I equals I1 plus I2 is equal to I3. That is the first equation. Considering the first loop, we saw that 10 is equal to negative 2I3 minus 6I1. That was the second equation. Considering the second loop, we saw that 10 minus 14 or negative 14 plus 10 was 4I2 minus 6I1. That was the third equation. If the examiner wants I1 and I2 may ask you to solve, but the examiner will always ask you to solve equations where the equations are easy to solve using simple substitution. So may I just put these three equations in my calculator? Of course, if you want to solve them simultaneously, you can rearrange them very well and say maybe you can say I1 plus I2 minus I3 equals to 0. That's one equation. Then you can say negative 6 I1 plus 0 I2 minus 2 I3 equals to 10. I'm just trying to rearrange them for you if you want to solve them. Then this one, of course, this one has given us negative 4. So I can say negative 6 I1 plus 4 I2 plus 0 I3 equals to negative 4. So we have these equations here. You just put them in a calculator, or you can use substitution method and see if you can solve I1, I2, and I3. I tried to solve and I got I1 as 2, I3 as negative 1, and I2 as negative 3. Of course, the minus just to show that the arrows, the direction of the currents chosen here are not correct. For example, if I1 is 2 amperes and positive, it means we chose the correct direction of current for I1. If I3 is minus 1 ampere, it means I would have chosen the correct direction of current to be in the opposite direction. If I2 is minus, it means I would have chosen the correct direction of current to be in the opposite direction. Okay, so note that I2 and I3 are both negative. This indicates only that the currents are supposed to be in the opposite direction to the ones we chose for them. However, the numerical values or the magnitudes will be still the same and will be correct. So that is how we use Kirchhoff's laws. Example number 2. You can always pause the video and you try to see if you can apply the laws to find the equations. In the figure, find the current flowing through 3 amperes, 3 ohms, 2 ohms, and 4 ohm resistors. You may use junction B, loop A, B, E, F, A, and loop B, C, D, E, B. So like I said, many times the examiner chooses for you the loops, and many times you will not be asked to solve these equations. But in case it happens, you should learn to use your calculator to solve those equations, or you should use our quadratic methods, or equations of substitution, elimination method, and so on and so forth to solve those equations. Many times when the examiner asks you to find the current, it's only because it's easier to solve the equations without using a lot of mathematics. Okay, you can always pause the video and try to see if you can come up with the equations using the first law at junction B. So at junction B, I is entering the junction, I1 and I2 are leaving. So at junction B, I can predict that I equals to I1 plus I2. That is in accordance to the first law. The sum of currents into a junction equals the sum of currents out of the junction. Then using the loop A, B, E, F, A. So I'm moving from A to B, there is no cell. B to E, there is a cell, but I start with the positive before negative, so this EMF is going to be negative. So the EMF there is going to be negative 3. From E to F, there is no cell. From F to A, there is a cell, but I meet negative before positive, so this EMF is positive, so this will be plus 10. That is the sum of the EMFs. Then when I talk about the PDs, I look at the resistors in that circuit, in that loop. So if I move from A to B, The current through 3 ohms is in the same direction as the loop because the loop is from A to B, then the current is also from A to B. So this is going to be positive. So this will be 3 times I. Remember the PDV is equal to I times R. Then from B to E, the current I1 is in the same direction as the loop. So this is going to be plus 2 times I1. Then from E to F, the current through 7 ohms, I is the same current here. This is I, this is I, this is I. So the current here is still I, this is still I, this is still I, because it's the same side of the circuit. So this will be plus, because the current is in the same direction as the loop, so this will be plus 7I. Or alternatively, I can say negative 3 plus 10, that is 7, equals to 3I plus 7I, which is 10I plus 2I. That is the equation from that loop. Then if I consider the loop B, C, D, E back to B. So in moving from B to C, there is no cell. C to D, there is a cell, but I start with positive before negative. So this EMF is going to be negative. So I have negative 5. D to E, there is no cell. E to B, there is a cell, but I start with the negative before positive. So this is going to be positive. So that is the sum of the EMFs. This should be called the sum of the PDs. So the sum of the PDs, I look at the resistors. From B to C, the current I2 is in the same direction as the loop. So the PD is positive, which is 4 times the current I2. C to D, the same current I2 flows here. This is I2. It is the same current here, I2. So the current through C to D, the current flowing is still I2. And it is in the same direction as the loop. So this is going to be 6 I2. Then D to E, it is the same current I2. The same current is flowing until we reach a junction. That's when it divides. So D to E, it is still the same current and is in the same direction as our loop. So it is going to still be positive 5 I2. But then at E, there is a division of current or splitting of current. So at E, from E to B, we see that the current flowing is I1, which is upwards. And from E to B, the current is in the opposite direction to the loop. So this is going to be a negative P, which is negative 2 times I1. Or I can summarize this as being 2, negative 2 being equal to 4 plus 6 plus 5, that is 15, I2 minus 2, I1. So that will be the equation for the sum of the EMFs being equal to the sum of the PDs. So I have one equation, 2, and 3 equations, which can be rearranged to come up with easy to solve simultaneous equations, which you can just run into your calculator and you solve to find the answers, or you can use substitution elimination method to solve or you can even use matrix if you're a good math student, but this is not necessary for physics. So at B, we saw that I is equal to I1 plus I2. That was the first equation. Then we also got 10 plus negative 3 equals 3I plus 2I1 plus 7I, which was 7 equals to 10I plus 2I1. Then considering the second loop, we saw that negative 3 plus 5. So moving from B to C to D. So this is positive 3 plus negative 5. 3 is going to be positive, the other will be negative. So positive 3 plus negative 5 is equal to 2I. So in moving from B to C the PD was positive, C to D the PD was positive, D to E the PD was positive, then this was negative, which when we simplify, this gives us negative 2 equaling to 15 I2 minus 2 I1. So this was our second equation. So we can now solve these equations. The easiest way is to rearrange them. So I can say I minus I1 minus I2 equals to 0 because there are only 3 unknowns, so this is equal to 0. Then the second equation I'm rearranging, so it will be 10I plus 2I1. There is no I to solve, so plus 0I2 is equal to 7. Then the third equation, if I rearrange, it will be there is no I, so I'll say 0I plus, so it is negative 2I1. I'm just reorganizing the equations to come up with the simultaneous equations which are easy to solve. So negative 2I1 plus 15I2 is equal to negative 2. So if you are a very good mathematician, whichever method you use to solve these equations, like I said, it may not always be necessary to solve them in an exam, but if you're a good mathematician, you can try to solve these equations. So I try to solve them using my calculator. You can use substitution, it may take long. You can use matrix, you can use elimination, and so on and so forth. So solving the equations, I go to 0.575, 0.625, and negative 0.05 amperes. You can also try and see if you get almost the same answers. Okay, so that is example 2. This was part A. If a high resistance voltmeter is connected across BD, that is across BD, okay, what will be its reading? Okay, so in the second part, we have a high resistance voltmeter connected across BD. So we have a voltmeter between B and D. When we say high resistance voltmeter, it means no current goes through it. That's why I've put here I equals to 0. So I've taken part of the circuit that we had in part A. So there was a current here, which was I. It divided at the junction, but they say this was a high resistance voltmeter. So I'm going to assume if there was to be a current, maybe it would flow in that direction. But remember, this current is going to be negligible, approximately 0. So the current I2 is the same current flowing here because no current goes or is coming from the current from here is 0, so it doesn't combine with anything here. So here we have I2, the current is I2, it is the same current here which is still I2. Okay, so I've randomly chosen these loops. I've just randomly chosen the loops to be in one direction. One of my students told me that they realized that if the loops are always in the same direction, the algebra always became easier. Also, in part A, I arrived at the values of current I1. I think I1 was 0.625 amperes and I2 was 0.05 amperes. Okay, so the examiner expects that this is a very easy circuit to solve. So the algebra is easy if I have the currents. Of course, the examiner, if he wants you to solve this circuit, will give you the values of I1 and I2 because they don't expect you to solve for them in the previous example. So moving from B to E, E to D, D back to B, the sum of EMFs, we have only one cell, but moving from B to E, this is positive, negative, so the EMF there will be negative 3. There's no any other cell, so the sum of EMF will be negative 3. Then sum of PDs, moving from B to E, the PD is positive because the current is in the same direction as the loop. So this will be positive 2I1. Then E to D, remember the current through 5 ohms is I2, which is in the opposite direction. So this will be negative 5I2. Then in D to B, there is no current. Oh, I can't say that because I want to find the PD from D to B. I can't say the because there is no current and no the resistance is very high, so I will just say moving from D to B, I'm moving in the opposite direction to the would-be current, even though it is 0. So it means the PD from D to B would be negative, and I'll call it negative V. Then if I consider the other loop, which is B to C, Okay, let me first solve this because I know the current I1 and I2. I can just solve and find V. So if I make V the subject, V is going to be equal to -3 minus 2 times 0.625 plus 5 times 0.05, which equals to, I think this is positive. When I take V to the other side, 3 will be positive. 3 goes to the right hand side, so it is positive. And I've taken V, negative V to the other side, so okay. If I take negative V to the other side, then I have to bring 3 to the right hand side. So V is positive, 3 becomes positive. This remains positive, this remains negative. Okay, so I have 3 plus 2 times 0.625, then minus, so 3 plus 0.625, I think I got the current as negative 0.5, so this is minus 5 times negative 0.5, which gives us, so this is giving me 4.5 volts. Okay, so the current I2 was negative 0.5 from part A. You can check back. So it means this is negative, this is 4.5. I can also check, of course I expect to get the same answer if I choose another loop, the other loop which is below. So using the second loop, moving from B, say to C, to D, back to B, the EMF is going to be negative. B to C, no, the loop is the other way around. It is from B to D to C back to B. B, D, C back to B. So if I consider that loop, B, D, C back to B, so the EMF is going to be positive 5 equals to the sum of the PDs. The EMF is positive 5 equals to the sum of the PDs. I'm moving from B to D. So here the PD is going to be positive V, because D to B was negative V, so B to D should be positive V. Then D to C, the current is in the opposite direction, so it will be negative 6 I2. Then C to B, the current is in the opposite direction, so it should be negative 4 I2. So remember I2 was 0.625. So if I solve this, I should be able to get the same thing. So let me check. So V is going to be 5 plus 10 I2, which I2 is 0.625. So I said 10 times 0.625, and sorry, the current is 0.205, not 625. So I have 10 times negative 0.05, then plus 5, which gives us 4.5. Okay. Okay, so I think this is what we have just obtained. From the first loop, we got that V is equal to 4.5. Remember I said we had got I1 as 0.6525 and I2 was negative 0.05. So when I substitute for I2, this becomes a plus, which gives us 4.5. And I said alternatively, I could use the other loop, B, D, C back to B, where we saw that the PD, B to D, the PD is positive V because we said D to B was negative. So moving from B to D should be positive. Then D to C, there's one cell. We are moving in the same direction as we are meeting negative before positive terminal. So this is going to be positive 5. Then the PD is in the opposite direction. The current is in the opposite direction to the loop, so the PD is negative 6 I2. Then for 4 ohms, also the current is in the opposite direction to the loop, so it is negative 4 I2. And when I substitute, I still get 4.5. So in both cases, this is still going to be 4.5 volts. Okay, that is simple algebra. The examiner, if he gives you currents, he expects you to be able to solve such a question. Okay. Example 3. In the diagram, V is a high resistance voltmeter. Find its reading. So to find the PD V, or the reading of the voltmeter, first of all, I can find the current in the circuit. Because it's a high resistance voltmeter. I can assume that the current flowing through it is approximately 0. But I can draw a loop in here. I can draw a loop which eliminates the voltmeter to find the current. Maybe I will say this loop is going to be anti-clockwise. So in other words, I have a circuit where the voltmeter has been ignored, so I have a continuous loop. So this is going to help me to find the current. I've randomly chosen the direction of the current to be in this direction here. So the current is in that direction randomly. So if I consider Kirchhoff's laws, there are two cells moving in the direction I've chosen. I move from, let's say, A to B to C, D back to A to B, B to C, this makes the EMF to be negative. C to D, there is no cell. D to A, it makes the EMF to be positive. So it means the sum of the EMFs is going to be 10 plus negative 4. That's the sum of the EMFs. Then sum of the PDs, A to B, there is no resistor, so no PD there considered. B to C, there is a resistor of 4 ohms, but the current is still the same. It is still I. The same current I is flowing everywhere because there is no current going through the voltmeter since it was high resistance. So the PD across this is going to be 4I, and then for the 2 ohms, the PD is going to be 2 times I. So this gives me the current in the circuit as 10 minus 4, which is 6, divided by 6. So it means the current in the circuit is going to be 1 ampere. So now I know the current flowing. Or I could also, since I can find a total EMF, then I could use the total EMF and I find total resistance because they are resistors in series. Total EMF is 10 and 4, but they are not aligned. They are not the cells are arranged in different directions. So one should be positive, one negative. So total EMF is positive 10 plus negative 4. Total resistance, their resistors are in series, so it will be 6 plus 2. Then I said the current is going to be the total EMF over total resistance, which will still give me 6. So if I consider that loop, we have saw that the current is 6 amperes, or I said I could use the concepts of total EMF and total resistance, and I know that current is equal to the EMF over total resistance, which still gives me 1 ampere. Then I now know the current. I now have to find the PdV, or the PD potential between Q and P. So in that case, therefore, I have to choose either the left-hand side of this circuit or the right-hand side. They should give me the same thing. So I'm going to consider a loop, either loop 1, which is on the left-hand side of the circuit, or loop 2 on the right-hand side of the circuit. So moving in the loop which I have chosen, which is anti-clockwise, say from this point here, let me call this A, Q, P, D, back to A. Moving from A to Q, Q to P, P to D, D back to A. Then we notice that there's only one cell which is moving from D to A, makes the EMF to be positive 10 volts. There's no any other cell. That is the sum of the EMF is 10. Then sum of PDs, A to Q, there is no cell, there is no PD. Q to P, because we are assuming if there was a current flowing, it would have flown from Q to P. So this is going to be positive V. The PD there is positive. If I say P to Q, then the PD would be negative, but Q to P, let it be positive. Then from P to D, D to A, there is one resistor of 2 ohms. So the PD, remember the current was flowing in that direction. So the PD is positive because the current is in the same direction as the PD. So this would be plus 2I. Remember I is 1 ampere, so if I substitute 1 ampere, it means the V is going to be 10 minus 2, which gives me 80 volts. I should get the same answer if I consider the right-hand side. So if I consider the loop I have just chosen randomly, loop 2, let's say it is Q to B, this is C, this is P. So I'm saying it is Q to P, P to C, C to B, B to Q. So if I consider that, I could also have chosen it the other way around, I would get the same answer. But let me just follow the one I've drawn in here. So Q to P, the PD will still be positive. P to C, there is no cell, there is no PD. C to Q, there is a cell of e.m.f 4, and this e.m.f is positive. Because I'm starting with the negative before positive terminal, so the e.m.f is positive. Sum of PDs. C to B, the PD is positive, because remember the current I was flowing in this direction, so the PD is negative, so it will be negative 4 times I. The current I was flowing in this direction from the previous circuit. Then Q to P, the PD is positive, so it is positive 4V. Positive V. So when I substitute for I, remember I was 1. So it means 4 is equal to negative 4 times 1 plus V, which still means that V is going to be 80 volts. So in both cases, whether I use the left-hand side or the right-hand side, I get the reading of the voltmeter to be 80 volts. These are the most important questions you need to become careful with, or you should become serious with. Okay, so here I've given you a trial example, but I'll try to solve this because you will have more questions to practice. In the figure below, write down equations relating the current at Roman 1 at A, Roman 2 at B, Roman 3 at C. So at A, at junction A, the current entering is 3 amperes, leaving is I1 and I2. So I'll say 3 equals to I1 plus I2. Sum of current to the junction equals sum of current out of the junction. Roman 2 at B. So this is B. I1 is coming to B. This is I1. 0.1 is leaving B. I3 is leaving B. So I can say I1 equals to I3 plus 0.1. Then Roman 3 at D. So at D we have 0.1 coming to D, I2 is coming to D, and I4 is leaving D. So I can say sum of currents entering equals sum of currents leaving. So I4 is leaving should be equal to I2, which is entering, plus 0.1, which is also entering. Okay, write the equations relating EMFs to PDs in each of the loops shown. So loop 1, so this is B. Let's look at loop 1. In loop 1, there is no cell, so the sum of the EMFs is going to be 0. There is no cell. But in loop 1, moving from A to B, the current is the same direction as the loop, so the PD is positive, so that is 12 times I1. Then B to D, the current is in the same direction as the loop. The resistor here is 10 ohms, so the PD is going to be plus 10 times 0.1. Then D to back to A, the current I2 is in the opposite direction to the loop, so the PD here is going to be negative 16 times I2. So in other words, I can say I can simplify this and say 12 I1 minus 16 I2 or plus 10 times 0.1 is 1, should be equal to 0. That is an equation we are talking about. Then that was the first one. Then loop 2, the sum of EMFs. There is no cell, so the EMF is 0. Sum of PDs. Now look at the loop. The loop is clockwise, so it is D to B, B to C, C back to D. So D to B, the current is downwards, the loop is upwards. So that is going to be negative 10 times 0.1, which is negative 1. B to C, the current I3 is in the same direction as the loop. So the PD is going to be positive 15 times I3. C to D, the current I4 is in the opposite direction to the loop. So this is going to be equal to negative I4 times R. So this is going to be this equation for loop 2. Then let's look at loop 3. Loop 3, there is a cell whose EMF is X. So we can say the EMF of the cell is X equals to, when I move around the loop, from C, I have to move around up to A. There's no resistor there. But then from A to B, we notice that the current is in the same direction as, the current I1 is in the same direction as the loop. So that is going to be positive 12 I1. Then from B to C, the current is also in the same direction as the loop because we're moving from A to B, B to C, back to A, moving through the cell back to A. So B to C, the current is in the same direction as the loop, so this will be plus 15 I3. I think those are the only PDs we have in that loop. So this will be the sum of the EMFs equals the sum of the PDs. So those are going to be the equations considered here. Like I said, the examiner may not always ask you to solve these equations, especially if they are very complex, or if they have 3 unknowns and they involve a lot of mathematics. Okay, in the figure below, write down equations relating the currents at A and at B. So at A, where is A? A is here, I is entering, I1 is leaving, I2 is leaving. So Roman 1 at A, we have I is entering, should be equal to I1 plus I2, that is the sum of currents into a junction, equals the sum of currents out of the junction. Then Roman 2 at B, B is here. We see that I2 is entering, I2 is coming in, the rest are leaving. So the sum of currents into a junction, which is I2, should be equal to I3 plus I4 plus I5. Write the equations relating EMFs to PDs in each of the loops shown. Okay, let's start with the loop 1. Now you are becoming experts in writing out EMFs and PDs. Loop 1 is anti-clockwise. So loop 1 is from A to E, E to F, F back to A. When I move from A to E, E to F, F back to A, the EMF is positive. So this is going to be positive 50 volts. That is the sum of the EMF. Sum of the PDs. A to E, the PD is positive because the current is in the same direction as the loop. So that is 8 times I1. E to F, the PD is positive because the current I is the same current here. This is still I. So this is going to be plus 8I. Then we have an internal resistor here, a small resistor here, which is 1 ohm, and the current through it is I. And it is in the same direction, the current through it is in the same direction as the loop, so it is going to be plus 1 times I, which is simply I. Or you can simplify this and say, okay, this is 50 equals to 8I1 plus 9I. Okay, that's loop 1. Let's look at loop 2. Loop 2, we have, there is no cell, so the EMF is 0. Then PDs. moving from the loop is anti-clockwise, so it can be A, B, B to E, E back to A. So A to B, the current is in the same direction as the loop, so the PD is positive. We shall say 8 times I2 plus B to E, the current is in the same direction as the loop, so it will be 8 I3. E to A, the current is in the opposite direction to the loop, so it will be negative, so it will be minus 8 I1. So that is the equation for loop 2. Let's look at loop 3. There is no cell, so the EMF is 0. Then the loop is clockwise, so I can say B to E, E to D, D to back to B. That is clockwise. So if I say B to E, the current is in the same direction as the loop, so the PD is positive 8 I3. E to D, the current is in the opposite direction to the loop, because this is the current. So the current is in the opposite direction to the loop, but this current was not labeled. Which current is this? So for simplicity, let me just call this I6. However, this would be the current at D would be I5 is entering, I4 is entering. So I5 plus I4 is equal to I6. So even if I don't know this current, I can just put there I6 is equal to I4 plus I5. I could just put this in brackets, but I will just call it I6. So 0 equals to 8 I3. And from E to D, the current is in the opposite direction, so which is going to be minus 8 I6. Then from D to B, the current is in the opposite direction, so I'll say minus 8 I4. As long as the current is in the opposite direction to the loop, also the direction of the circuit, of movement around the circuit, the PD is negative. So this will be the equation for loop 3. Let's talk about loop 4. I'm only doing this so that I give you confidence in coming up with these equations. So loop 4, there is no cell, so the EMF is 0. So PDs, this is clockwise, so I can say B to D, D to C, C back to B. So D to B, B to D, the PD is in the same direction as the loop. I mean, the current is in the same direction as the loop, so the PD is positive 8 I4. D to B, the current is I5. I5 is flowing that direction. So D to C, the current is I5 and is in the opposite direction to the loop. So this is negative 8 I5. Then C to B, the current is in the opposite direction to the loop. So it will be negative 8 I5. So I think that is all. So that will be the equation. Okay. Like I said, you may not always be asked to solve such an equation in an exam or such equations in the exam, especially if they are very complex. Okay. Self-check. Here is a self-check. So the self-check questions are very easy. I may give you a hint where possible, but at least by now you should be very confident. So this question here, you can solve it using both Kirchhoff's laws and just simple combination. Find the effective resistance. You can try to use Kirchhoff's laws if you are now very confident with them. Of course, if you are using Kirchhoff's laws, there is no cell here. EMF here will be 0, EMF here will be 0, EMF here will be 50, depending on the direction of the loops you choose. However, if you don't follow Kirchhoff's laws, remember these two are in parallel because they have two common points. So you combine them as 6 times 6 over 6 plus 6, which give us, I think they give us 3. So this become one resistor, which is joined to this point here and joined to the other point. So it becomes one resistor of 3 ohms joined to that point. So the resistor of 3 ohms is going to be in series. It's going to be in series with the 6, which gives us 9. 9 is going to be in parallel with the 6, which gives us 6 times 9 over 6 plus 9. And this gives us 6 times 9 divided by 6 plus 9, which gives us 3.6 ohms. 3.6 is in series with the 6. So I'll just say plus 6, which gives me 9.6. But then there was an internal resistance of 0.4. So I just say plus 0.4, which gives me 10. So when you become an expert, you can combine that very easily. If it is hard to combine, then you can break down the circuit into smaller circuits. For example, when I combine those, I come up with one resistor, which is joined to 6 ohms. This is now 3 ohms, 6 ohms. So one resistor is joined to 6 ohms, but there's another resistor here. And then I have 6 ohms here. So I have something like that. So this and this are in series, which gives me 9. So again, 9 is in parallel with the 6 ohms. So that's why I said 6 times 9 over 6 plus 9. So I come up with another circuit. This is for amateurs, but you can still do it. So this is 9 and this is 6. Then these two again combine to form a resistor of 3.6. So you come up with another circuit like this, where you have a resistor of 3.6 instead of the 6 ohms. But there's the cell, something like that. Remember, the cell has a resistance of 0.4 ohms. So now we have 1, 2, 3 resistors in series, which combine to form a 10 ohms. Then the power dissipated, of course, power equals to I squared times R. All we need is to find the current in the circuit, in the battery. The current in the battery is equal to the EMF divided by total resistance. Total resistance is 10, the EMF is 50, so it is 50 divided by 10, the current is 5 amperes. So if the current is 5 amperes, so it means the power is going to be 5 squared times the resistance of the battery, which is 0.4. We want power dissipated in the battery. Resistance of the battery is 0.4. That is internal resistance. So let me check 5 squared times 0.4. That is 10. You can also verify this. Okay. In the diagram, V is a high resistance voltmeter. Find the reading. I have done a similar example where I said 1. I can first ignore the voltmeter and put in a circuit, a loop, such as that one, which is anticlockwise, to find the current. Because it's a high resistance voltmeter, no current flows through it. So if I put in such a loop, I get the current. Let me say the current is I. So putting in such a loop, moving anticlockwise from A to Q to B, C, D. A to B to C, the EMF here is negative 8. D to A, the EMF is positive 12, should be equal to the PDs. The current through 2 ohms is still I, so it is 2I. The current is in the same direction as the loop, so it is 2I plus 4I. So this gives me 4 equals to 6I, which means the current is 4 divided by 6, which is going to be 2 over 3 amperes. That is the current, or which is 0.67. Then I want the voltage, so I will take part one side of this circuit. Maybe let me take the left hand side. So I'm going to take the left hand side of the circuit. Of course, even if you take, the right hand side of the circuit, even if you take the left hand side, you should be able to get the same answer. Remember, the current here was I, which is 2 over 3. The same current was flowing. There was no current through here. Here the current was 0. And the voltmeter is somewhere here. So this is 80 volts. This is 4 ohms. So I'm going to put in a loop, which is maybe anticlockwise. So I now know the current flowing. So if I move from, say, this is Q, B, C, P. If I move from Q to B, B to C, C to P, P to Q, there's only one cell, so the EMF is going to be -8. According to the loop I've chosen, I could have chosen it to be clockwise. The answer would be the same. So the EMF is 8. Then the PDs, Q to B, there is no resistor. B to C, the loop is in the same direction as the current, so this is going to be 4 times I. C to P, there is no resistor. P to Q is in the opposite direction to the one I've chosen if there was to be a current through the voltmeter, so this would be -V. The PD will be -V. So I want to make V the subject. So V is going to be 4 times the current, which is 2/3 plus 8. So I have 8 divided by 3 plus 8. So this gives me V as 10.7 volts. You could get the same answer if you chose the left-hand side. You can try that on the left-hand side. Apply Kirchhoff's laws and see if you can't get the same answer. In the figure, find the current flowing through 2 ohms, 3 ohms, 6 ohms. Use loops A, B, E, F, A. So you are going to use that loop. And B, C, D, E, back to B. Of course, you must come up with an equation for current. You can choose the current randomly. Let me just choose for the currents maybe. Let's say this is I1. I'll say this is I2. And maybe let me say this is I3. This is entering, this is entering, this is leaving. So this is just for practice. You can try to find the currents I1, I2, and I3. Of course, you must use Kirchhoff's first law at the junction, and then you use Kirchhoff's second law using the loops. You should be able to come up with the currents. I will not solve that because I've done an example. Use Kirchhoff's first law to deduce the values of the current I in the figure. I'll just press my calculator and give you the answer so that you'll be able to use the law to find if the answer is correct. So I'll say, I think the answer here is going to be 7. I think the answer there is 4.5 amperes. You can check it. Then here, I think here the current through X is going to be 1.5, and it should be into 1.5 amperes into the junction. You can verify that. C, calculate the sum of currents in and sum of currents out in the figure. So sum of currents into 1, 2.5, 3.5. I think I into is equal to 6.5 amperes. You can verify sum of currents out is 4 plus 0.5, that is 4.5. Sum of currents out, I think it's also 6.5 amperes. You can verify. Deduce value of X. I'll just press my calculator. So Ix is going to be equal to -2 amperes. The negative means the arrow is supposed to point towards the junction. You can also verify that. Deduce the PD across the resistor R in the circuit and hence find the value of R. I think this is a very easy question because we have done several examples. Deduce the PD across the resistor R. We know the current, we know the EMF. Okay, so it is easier for me to find the PD across this one because I know V is going to be equal to I times R, which will be, for 20 ohms is going to be 0.1 times 20, which is going to be equal to, I think that is 2 volts. But remember the supply is 10 volts, so it means the balance should be to R because the 10 volts is divided in the ratio of the resistances. So the PD here is going to be 10 minus 2, which is equal to 8 volts. So that is 80 volts. Find the value of R. Since the current is the same, 0.1 amperes, so it means the resistance is equal to V over I. V is 8 over I, which is 0.1, which gives you 80 ohms. You can verify. No doubt you could find this without applying Kirchhoff's laws, so I have not applied Kirchhoff's laws. But you will find the law more useful for complex problems. I could have used the Kirchhoff's law, by the way, here in this equation, and I find the answer. If I put in a loop, the sum of PDs is going to be 10 volts. I mean the sum of EMFs is 10 volts. Sum of PDs is going to be 0.1 times 20 plus 0.1 times R. That would give me the resistance, of course, as 8 still. Then find I in this case. There are two ways of doing this. You could put in a loop, Kirchhoff's law, second law, and you find the sum of the EMFs. Note that this is positive, negative. So this is negative, this is positive if I move anti-clockwise. So the sum of EMFs is 6 minus 2. Should be equal to the sum of PDs, which is 10 times I plus 30 times I. So I is going to be equal to 4 divided by 40, which is 0.1 amperes using Kirchhoff's laws. Alternatively, you can find effective EMF and total resistance, and current is equal to effective EMF divided by total resistance. Calculate the current in each resistor. I don't know whether this is necessary to solve, but such a question may be very hard for most of us. However, it is easier to solve this if you use Kirchhoff's laws. Because here it will be hard for you to combine these cells, this one and the other one, because they are not linked. And you can't say they are in parallel. You cannot say they are in parallel. However, if I put in a loop, I choose a junction, let's say the current is coming from there. Let's say this is I, this is I1, and this is I2. So I can say that I is equal to I1 plus I2, that's number one. Number two, I'll put in loops. Let me put a loop here, which is which is clockwise. Let that be loop one. So if I consider loop one, which is clockwise, the EMF is positive, which is going to be 2.0. Should be called the PDs. So the PDs, we have only one resistor of 30 ohms. So this is going to be, and it is in the opposite, it is in the same direction as the loop, because the loop is clockwise. I'm moving from A to B to C to D back to A, which is clockwise. And the current I1 is in that direction. So I will say this is equal to 30 times I1. So it means I know I1. I1 is going to be 2 divided by 30, which is 0.067 amperes. That is the current through 30 ohms. Then if I want to find I2, I have to first find I. So to find I will put another loop here. Let me say it is also going to be anti-clockwise. So the sum of the EMF, there's only one cell of 6 volts, which is positive, should be equal to the sum of the PDs. For the PDs, we have 30 is in the same direction, the current is in the same direction as the loop, so it is 30 times I1. But the current in 10 ohms is I. So this is I. So this is going to be plus 10 times I, because the current I is the same current through 10 ohms. So it means I will simply say I is equal to 6 minus 30 times I1, which I1 was 2 over 30. Then I will divide this by 10. I'm making I the subject. So 4 divided by 10, I think it is 0.4 amperes. So I is 0.4 amperes. So the current in 10 ohms, 10 amperes is, the current in 10 ohms is going to be 0.4 amperes. If I wanted to find I2, which may not be necessary, so I2, okay, I don't need to find I2 because I want the current in each resistor. So in 10 ohms it is 0.4, in 30 ohms it is 0.0067. Okay, so this is not even necessary, but this would be I2, I think. That would be I2. Okay. Below is the network of resistors, and our current passing through the end resistor is I1 is 1 ampere. Show that the PDV across the input terminals is 13 volts. Show that the PDV across the input terminals is 13 volts. So we want to show that the PD here is 13 volts. So you can combine the resistors naturally to find total resistance. If you're very good at combining resistors, you know that these are in series, so total is 2. 2 is in parallel with 1, so you say 2 times 1 divided by 2 plus 1. Then the one you have got is in series with 1, so I'll say just plus 1. The one I get is in parallel with this one, so I'll say times 1 divided by answer plus 1. The one you get is again in series with this one, so I will say plus 1. So total resistance is 1.625 ohms. That is total resistance. However, this will not help you to find the value of V, because V is equal to the you don't know the total current, so you don't have the total resistance. You have two unknowns. However, if I use Kirchhoff's laws, I put in loops here. Let me say this is, I'll put in the loops in the same direction as suggested by my students, that whenever the loops are in the same direction, the algebra becomes very easy. So when I look at loop 1, there is no cell, so EMF is 0. Then PDs. So the current all here is 1 ampere. Let's say the current 1 ampere comes here. I'm going to start from here. Let me say this is I. Let this be I1, I2. So at this junction, remember this is 1 ampere. Let this be I3. So it's like the current here is going to be I3 plus 1. Okay, so using loop 1, EMF is 0. Now I'm looking at PDs. So I have positive, positive. So 1 times 1 plus 1 times 1. So this is going to be 2. Then for I3, it is in the opposite direction to the loop. So it will be minus I3 times 1. So it means I3 is equal to 2 amperes. Let me look at loop 2. I3 is equal to 2 amperes. Of course, it means I1 is, this implies that I1, remember I1 is at the junction, is equal to 1 plus I3. I1 is 1 plus I3, which is going to be 3 amperes. So I1 is 3 amperes. So the current here is going to be equal to 3 amperes. Then when I consider loop 2, there is no cell, so the EMF is 0. PDs. I3 is in the same direction as the loop, so this is going to be I3 times 1, which is I3. Then I2 is in the opposite direction to the loop, so this would be minus I2 times 1. I1 is in the same direction as the loop, so this would be plus I1 times 1. So remember, I3 is 2, I2 is not known, I1 is 3. So this means that I2 is going to be equal to 5 amperes. So I know I2 is 5 amperes. Note that from this junction here, I equals to I1 plus I2. So I equals to I1, which is 3, plus I2, which is 5, which gives us 8 amperes. So total current is 8 amperes. So using loop 3 now. Loop 3, the EMF, let's say this is positive, this is negative. So this is in the same direction as the loop. So this is going to be V as the EMF. This is going to be equal to the PDs. 1 ohm, the current is I, so it is I times 1, which is I times 1, which is I. Then we have this one in that loop, which is I2 times I. So this is plus I2 times I, which times 1. That is all. So it means the V is going to be I, which is 8, plus I2, which is 5. That gives us 13 volts. Okay, so that is a multiple choice question, I'm very certain. And using Kirchhoff's laws, it is easier to find. Lastly, or last but not least, this is for you to try out. This question was set by my favorite student I've ever taught. So in memory of the best student I have ever taught in my life, show that the PDV across the input terminals is 172 volts. So this student sat down and just modified a circuit and came up with a more complex circuit, and we were able to verify that the answer is 172 volts as a class, or he was able to verify to the class that the answer is 172 volts. It is just for practice, not for examination purposes, but you should be able to find you should be able to show that the PDV is 172 using the previous example I've just done. Then you find the effective resistance in the circuit to 3 significant figures. So of course, if you have the EMF as 172, then of course you'll be able to, by the time you reach 172, you'll have the total current. Because in the previous example here, I could find, if I have the total current I is 8. If I want total resistance R, will be equal to the EMF divided by total current I. So the EMF we have got it as 13, total current is 8. So we shall say 13 divided by 8, which is 1.625. I think we had got 1.625 early on when we just combine them manually. So still here, if you have the current in this part here next to the battery, that is total current. The current from here is going to be the total current. If I have the total current and I have the EMF, remember total current is equal to the EMF divided by total resistance. You should be able to get the total resistance as the EMF divided by total current I. That is a food for thought. Until next time, see you in the last lesson of electricity.